では、皆さんお集まりいただきありがとうございます。第44回のチェーンセミナーを、行いたいと思います。本日は、ドイツのバイロイト大学から、ティモ・シュパイト先生に、講義を行っていただきます。簡単に、シュパイト先生を紹介しますと、シュパイト先生は、バイロイト大学の、哲学、コンピューターサイエンス、アーティフィシャルインテリジェンス、哲学、計算科学、人工知能講座の、講師です。専門は哲学と計算科学で、近年は、マシンエシックスであったり、マシンエクスプレイナビリティ、説明可能性などの分野で、多くの論文を出版されています。で、本日は、その説明可能性、AI の説明可能性に関連する講演をしていただきます。本日、講演は、英語で行っていただきますが、質疑応答に関しては、もし、必要であれば、できるだけ私が頑張って通訳をしますので、日本語で、質問をしていただいても結構です。では、皆さんよろしくお願いします。Okay, Timo, so I just briefly introduced you to the audience, so I'll give the Zoom to you.
Thank you
it's shared on the screen. Yeah. Yes, it's shared, I guess. Yes.
It should be shared. Yeah. So thank you for the kind, thank you for the kind introduction and welcome everyone. I want to talk today about making AI understandable, the gold methods and open challenges of explainable AI. So this talk is basically thought of as a as an introduction to my main research field, which is explainable AI, and it builds mostly on one previous publication of mine, which was published in 2021 in Artificial Intelligence. But more on that later. So basically the goal is that after this talk, you have a good understanding of what explainable AI is about. And without much further ado, let me get into the talk. Just a brief introduction or like a brief motivation. I mean, we are here in a research center for, among others, AI. And AI is ever increasing in our everyday life. So we have vacuum cleaners based on AI. We've got auto-completion of sentences in our mobile phones. But we also have AI that looks whether people should get hired, or AI that should decide whether coma patients live or die, so whether they are life-upholding machines will be terminated or not, and AI that is used in court. So we have a wide range of different AI systems applied in different scenarios. And with this diversity of AI and with this diversity of application of AI, one notices that the range of stakes that is connected to these different fields is also quite diverse. So we have we have situations of low stakes, for instance, in everyday search queries or music selection, where nothing really hinges on whether the AI makes a wrong prediction. And we have AI used in situations where it could potentially destroy a human's life if the AI makes a wrong decision. And in these decisions, in these high-stake decisions, it's increasingly, or I think it's very important to answer the question of societal desiderata. So what do I mean with societal desiderata? I mean, basically, so for instance, when something goes wrong, we want to hold someone accountable so that this person might pay remunerations to, at least compensate for the wrong that was done to us, or, to a specific person. And, so this is like one of these societal desiderata. Others are fairness. So we want it to be treated fairly by AI. We want to, we want that the AI performance is high. So this is also one of these desiderata. So in general, what I mean with desiderata is like something that can be, it's basically a goal that we want the AI to have. It's like, and like I said, so especially in those situations of high stakes, it is very important to satisfy these societal desiderata. And just to make this clear, so we have opaque systems like AI systems. So it's not only the problem that they are used at all places, but also that we do not know their workings very well. And this raises technical, moral, and legal challenges. We place desiderata on interacting with these systems. So for instance, trustworthiness, or that humans are still able to act autonomously when interacting with AI systems. We want responsibility, attribution, and naturally we also want that fundamental human rights and fundamental moral rights are upheld when AI is deployed. And so how does this connect with explainable AI? So one typical way that many researchers see to satisfy these desiderata is by so-called opening the black box. So we have highly complicated AI systems that many people do not understand and that make these consequential decisions. And to at least get a little bit of insights, or for instance, to see where the fault originated, we have to be able to look into these systems. So the goal is not to have a closed black box, but to have like this kind of white box where we can look into the system and see where the decision originated from. So basically we have to understand these systems. And many people see explainable AI as the way to lead to understanding AI. Good. So far, so good. That was the motivation. So we want to satisfy desiderata. And as I've already alluded to, basically, we seem to have to understand these AI systems to satisfy these desiderata. Now, the claim is that explanations or certain types of information that serve as in an explanatory role, that these explanations facilitate understanding. And basically, we have to have like some kind of approach or some kind of method to provide these explanations. So, and this is basically, the way I structure the field of explainability or the field of XAI when I approach it. And this is also how I will approach the field in this presentation. So we will walk starting from desiderata satisfaction, our understanding, explanations to the different approaches there are. And also a little bit because, I mean, what does it all bring if at the end we have an explainability approach, but the desiderata are not satisfied? We have a little look at if the times is still okay. How this might feed back again to the development of explainability approaches. So let's have a look at desiderata satisfaction. So if we want to satisfy desiderata, we first have to look at the people who might have desiderata with regards to systems. And so like, here's a very basic, map of the different stakeholders that might be involved in the deployment of AI systems. So we have in the center, we have the AI system that interacts with the user. We have a developer that basically creates the AI system. We have deployers, like for instance, some companies that bring an AI system into use and thereby create this interaction between users and AI systems. In the interaction between user and AI system, we have certain parties that are affected by the decisions of an AI system. And this whole interaction between developers, deployers, users, and affected parties is regulated by regulators. So this is like a very simple image of how, of what different types of stakeholders are involved here. But this can already give rise to a very large table of desiderata. So this is basically work. Okay, it's very small, so I hope it's readable. So this is basically work that I did where I analyzed over 100 articles on explainability and extracted what different people and different scholars claim on what could explainability, where it could help. So it could help for the acceptance of systems. It could help in accountability questions, like I already said. Explainability might help to increase the accuracy. What's there? Or it could also serve educational purposes. Some people claim that explainability can increase the how ethical a system is, or it can increase the robustness of systems. Likewise, it could also increase trust or trustworthiness. So there's like a huge amount of publications that have some claim with regard to how explainability or how XAI could, which desiderata are connected to XAI. But what's interesting is that most of these papers just claim that this interaction is there, and only a very small amount try to really empirically validate these claims. And in many cases, these claims are also inconclusive. So here one already sees like the first open challenges with regards to explainability, so that there are like many claims that explainability might be a panacea for reaching all these important desiderata, but there's not much empirical research that really tries to validate these claims. Okay, quickly going back to our stakeholders. So just to make these desiderata a little bit more graspable. So what does opacity mean for users? So for instance, if a system is opaque, the user might not be able to adequately calibrate trust. So they don't know whether they can trust the system or not. People affected by decisions of algorithmic of AI-based systems, they might have an impacted perception of justice. They might wonder about questions of fairness. Likewise, deployers might want that their systems are accepted, but the opacity of the systems might impact that. Developers try to ever increase the accuracy of their systems, and if they do not know why a system failed, it's hard to improve the performance or the accuracy. And finally, regulators might want to audit systems, but if a system is a black box and no one really knows what it does and why it does what it does, then this auditability is also impacted. So so this is like a brief overview of the different desiderata and the stakeholder classes. And I mean, then I'll always just like after one of these, after like getting into detail on one of these terms, I just briefly like highlight a few open questions. So one could ask, are these all classes of important stakeholders? Are there any other classes that we might have to consider? Does it make sense to classify stakeholders in this way, or should we like try to look at another way? Are these all important desiderata? So basically what I did was look into the literature, but the literature might not have everything there is. So there might be other important desiderata that are overlooked still. What is also interesting, and which will be like a recurrent topic, is that XAI is a topic that is currently handled by many different disciplines, from HCI to philosophy to pure computer science to psychology. And yeah, while reading all these papers and trying to extract desiderata from them, was very interesting to see that these different disciplines have different usage of words, of terminology. So basically, it's not often the case that one and the same term that could mean a desiderata is conceptualized the same way between disciplines. Then we could ask, are these desiderata justified? So for instance, we might see that a deployer wants that the system is accepted, but if the system is not a good system, then maybe this is not a justified claim. Yeah. So this is basically on desiderata and their satisfaction. And yeah, now the next part is how understanding is supposed to increase this desiderata satisfaction. Yeah, and here I normally make a distinction that desiderata can be satisfied in two different ways. On the one hand, they can be satisfied epistemically. So this basically means that, for instance, if my desideratum is that a system is fair, then understanding the system better will not make the system fairer, but understanding the system better will give me access to see whether the system is fair. So this is basically what I mean with epistemic desiderata satisfaction. So I can look into the system and understand whether a certain desideratum is satisfied. On the other hand, some desiderata can also be substantially satisfied by understanding the system better. So if I understand the system better, then I might be able to better allocate responsibility. So the desideratum of responsibility can, by understanding the system better, be substantially satisfied. Okay, like another example is retain autonomy. So I can, by getting explanations of a system, I can see whether I'm autonomous and can retain my autonomy, because I might be able to better, to make better decisions. On the other hand, if my goal is to see whether a system adheres to ethical principles, then just understanding it better does not lead to a better adherence to ethical principles. Yeah, so only the epistemic side is, so the desideratum is only epistemically satisfied. But yeah, by understanding the system better, one might improve the system and have like a basis for improving the system. So an epistemic desiderata satisfaction can be the basis for a substantial desiderata satisfaction in the long run. Good. I mean, understanding as such is a very difficult concept, which I might not really need to tell you. I mean, in the philosophical debate, it's normally agreed upon that there are different breadth and depths of understanding, which are normally subsumed under the term of degrees of understanding or extents of understanding, and there are different kinds of understanding. Normally, yeah, we have to, normally when we look at how psychologists examine understanding, then one can see that it's done via mental models. So basically, psychologists try to look whether the user's mental model of a system corresponds to what the actual system is about. And this can be elicited, for instance, in think aloud techniques, or by having the users paint a mental model, the mental model they have of the system, and then one can check whether they really have the right model. Another possibility that I thought about and just published is that one might measure understanding with testing for abilities. So basically, the more abilities a person acquires respect to a system. So for instance, if a person can assess whether the prediction is correct, then this is maybe less, then they may understand it less than if they are even able to predict what the system will do next, or if they are even able to explain and intervene into the system. Yeah. But yeah, so basically, yeah, these are like a few ways to elicit understanding. And now the interesting thing is that understanding a system does not always have to be good. So, I mean, yeah, it is always good in a way, but it does not always lead to desiderata satisfaction. So basically the connection between understanding and desiderata satisfaction is not as straightforward as it might, or as I might have alluded to. So I want to give like 3 short examples of what could happen. So imagine we want that the desideratum is to increase the trust in the system, but by understanding a system better, I might notice that there are like faults with the system, and then this decreases trust in the system. And yeah, this example actually brings me a little bit back to the question of whether desiderata are satisfied. So for instance, just like blindly increasing trust into a system is not a well-justified desideratum, because what we want is that a user's trust in the system is well calibrated so that they have the right amount of trust in the system. And by, yeah, basically, if the trust diminishes based on explanations because the users get to know that the system is faulty, then this is a good thing in a way. But yeah, at least maybe the deployer has a desideratum that, yeah, the trust should in any case be increased. Yeah. Another example is that desiderata can conflict. So we can imagine that another desideratum is to increase the transparency of a system, or the perceived transparency, and this might come to be with increased understanding of the system. But at the same time, the non-gameability of the system might decrease. So we can imagine like a system that is used in HR, so a system used for hiring people. If like an applicant knows how the system works, then this applicant might game the system. So the applicant might not be the best applicant, but as they know how the system works, they might evoke the best benefits for them. So this is basically that by a higher understanding of the system, the gameability diminishes. Yeah. And yeah, in both these, desiderata could be of the same stakeholder. So we could have a person wanting at the same time that the perceived transparency or the transparency of the system is high, whereas they do not want it to be gameable. On the other hand, we can also have cases where desiderata of different stakeholders might be in conflict. So again, we can imagine transparency, which might be a legal obligation, so that regulators want the system to be transparent, but at the same time that, yeah, because the system gets transparent and people notice that there are faults with the system, the acceptance of the system diminishes. So basically, desideratum of a deployer might diminish, whereas the desideratum of a regulator might increase. So yeah, so they are like interesting relationship between desiderata and the satisfaction. Yeah, and all these and whether like desideratum gets satisfied or not, yeah, is a very contingent matter. So it can always be influenced by contextual factors. So for instance, like I said in the beginning, the stakes can influence. So if the stakes are high, one might trust a system in any case less. even if it's trustworthy. Yeah, if one was subjected to a bad decision, so if I didn't get a job, then I might the question in any case, even if this decision was justified. So this is meant here by outcome favorability. Yeah, and these are just two examples of many. So yeah, so there's not that kind of a straightforward relationship between understanding and desiderata satisfaction. Yeah, and just to get into a few open questions again. Yeah, we can, I mean, these are just a few examples of trade-offs between desiderata, but there might be more. And what do these trade-offs imply? Yeah, how exactly does understanding and the degree of understanding we have relates to desiderata satisfaction? So as I've sketched with these big table, I've shown you that there's basically just claims in the literature that explainability will contribute to certain desiderata, but yeah, it's unclear how this really works out in the end. Yeah, I've shown you that contextual factors can influence this satisfaction. Yeah, then what does it mean for a desideratum to be satisfied at all? So, I mean, when can we justifiably attribute responsibility for a decision? I mean, then we have to clarify what does it mean for a person to be responsible? And yeah, we get back into all these philosophical questions, yeah, depending on which discipline one belongs to, maybe also legal questions. Yeah, and then again, how to maybe measure also this satisfaction. Good. So we've done half of the model. Let's continue to the explanations. Yeah, and I mean here, the most general claim is that explanation should lead to understanding, but that is mostly all that people agree on. So there are like many different kinds of explanations that people discuss. So for instance, teleological explanations, so goal-oriented explanations, nomological explanations, so explanations that depend on the laws of nature, statistical relevance explanations, contrastive explanations, so explanations that say why P happened and not Q, counterfactual explanations, yeah, mechanistic explanations, so explanations that appeal to some kind of mechanisms in the system, causal explanations, network explanations that appeal to the topological qualities of a system, and many others. And these explanations can be presented in many different formats. So we can imagine that they are presented as a natural language text. We can just extract maybe a rule from a system, or just like for programmers an execution trace, or even show people the source code. Or we can do it in graphics, visualizations, images, or even animations, or just sounds. Yeah, and again, depending on the context, it might differ how these explanations are processed. So, I mean, if we imagine explanations in an autonomous car, or maybe even in a normal car, then we might not want textual explanations, because this could, because people do not have like the capacity to drive and read textual explanations. But I mean, that's why navigating systems normally give you, yeah, a voice message in a way. Yeah, and so this is like a very short section, just because, again, I cannot really handle everything here, and most of this will like be a little bit offloaded to the part on explainability approaches. So what is interesting is that here, again, one can see that there are big differences between disciplines, because philosophers have, yeah, basically researched what explanations are for hundreds of years. But yeah, now computer scientists come into the game and yeah, basically have their own conception of what explanations are. And it's very hard to align what they see as explanations. So I will go into this a little bit later. Yeah, then the question is, how do explanations lead to understanding? how do we best, so what kind of explanations do we need to evoke understanding? How do how might stakeholder differences play out with explanations? And how again do like these contextual influences like stakes and where one is, so in a car or somewhere else, or like the time pressure one has, influence the relations between explanations and understanding. So how this influences whether one basically whether the explanation facilitates understanding. And then again, and finally, I mean, this all then plays out in the question of how explanations should be designed. Good. So, and now we come more or less after these like preliminaries, maybe we come to that what you might have imagined as a core part of the presentation. So what are different explainability approaches? So what is really discussed in the debate? How does that look like? And basically, there are three important distinctions, I would say, that we have to bear in mind when talking about XAI. And the first one is the distinction of stage. So basically, there are two possibilities, anti-hoc versus post-hoc. So what does this mean? Basically, anti-hoc is that we have an AI system that is already so easy, so simple that we can inherently understand it. Examples for this are decision trees. So normally when we traverse a decision tree, we can more or less understand what leads to a decision. So for instance, here's a little bit of a famous decision tree on that gives you the likelihood of surviving the Titanic, and it's best if you are like either a female or a boy under the age of 9. Okay, it's really small. Sorry for that. That has no siblings. But by traversing this tree, we can basically, with enough time, find this out. So it's like an AI model that is in a way inherently understandable. Other types of AI that are said to be inherently understandable or anti-hoc explainable, as some people would say, are linear models and also rule-based models. So I mean, rule-based models, I mean, we can transfer a decision tree in a rule-based model, and I mean, these kinds of models are normally treated as understandable or as explainable. However, I mean, it's a little bit questionable whether this is really true for all stakeholder classes. So whether really all stakeholder classes can extract information from these kinds of models. So I mean, if I imagine like a regular user or like just an affected party that has no computer science background whatsoever and has never engaged with computer systems, then I can already imagine that traversing such kind of decision tree, or even like seeing what a linear model does if one doesn't have like at least a little bit of a mathematical background, could be very hard. So it's really a question of whether these anti-hoc explainable models are explainable for everyone. Furthermore, I mean, if we imagine that this decision tree grows very big, or that the linear model has a little bit more of a complicated function, or that the rule-based model has many rules, then again, it's questionable whether this is really still explainable. And what is also often discussed is, I mean, why do we have deep neural networks? Why does everyone use deep learning? Because people say that these kinds of models, decision trees, rule-based models, and linear models, that they are not as highly performant, that they do not have as high of a performance as deep neural networks and other types of models. So there are difficulties with regards to anti-hoc explainable models. Let's come to the other possible stage, and this is basically the idea to explain the model after it was trained. Okay, I mean here like a very simple visualization of the basic mechanism of a deep neural network. So in these cases, we have that even sometimes experts don't understand how a network makes decisions. So there is a need for additional methods to extract information. So we need some kind of method to, that makes like basically the workings of this deep neural network understandable for us. These are like the explainability approaches. And this is basically where the second distinction comes into play. So I said there are three important distinctions. And for post hoc explainable models, we can have a second distinction, which is basically applicability. So there's a differentiation between whether the approach, the explainability approach I have is only applicable to certain kinds of models. So for instance, only to convolutional neural networks, or whether, these are the so-called model-specific approaches, or whether the approach can be applied to all kinds of models. So it doesn't matter whether it's like a regular artificial neural network, a deep neural network, or a convolutional neural network, a recurrent neural network, LSMT, or whatsoever. So it doesn't matter. And these are the so-called model agnostic approaches. And at the same time, and this is the third important distinction, I would say, there's a distinction between scope. And here the idea is, do I only want to explain a single prediction? So so I have like the prediction that this image here is a robot. Then the question is, so a local explainability approach would then give me an explanation just for this instance, or whether I want a global explanation of the system, so of the AI system, so how it globally works, then this would be a global approach, and this would explain the whole system basically. And as I won't go into global approaches too much, just like a very small, just a very small summary of basically how global models work. So the idea of global of global explainability approaches is mostly that they are built so-called surrogate models, so that they basically try to approximate the original model by an anti-hoc explainable model. So then the idea would be we have a complicated deep neural network, and we try to approximate the working of this neural network by building a decision tree that approximates this neural network, or by building a rule-based model that summarizes the most important rules. Good. So now I've given you all the theoretical details. So maybe now it's interesting to see that in practice. So one of the most famous explainability approaches you can find in the literature is LIME, so local interpretable model agnostic explanation. So here we can already see the name says us a little bit about these three distinctions. So it's local, and it's model agnostic, and it's post hoc. So so here the idea is roughly said that we it's mostly used, or I'll just like focus on visuals because that's easier for presentation, but LIME does not necessarily depend on visual data, so it can also be used with text recognition or something and else. The idea is basically of LIME is to segment in this case a picture into interpretable superpixels. So we have here like different superpixels, and then then it's basically some of these superpixels get disabled, so they will get turned black, and then the AI is queried again. okay, and it's looked whether the prediction changed. And the idea is, okay, if I deactivate an important superpixel, then the prediction of the class of interest should change. Should highly change. So and then basically in this way, one can find out which are the important superpixels. Okay. And this is then later on shown. So basically here we have an image of a dome. So that also gets the prediction that it is a dome. It's segmented into superpixels. And after applying Lime, we here get these superpixels that influence the prediction the most when they are disabled. There are like many kinds of saliency map that basically often depend on backpropagation. So it's about just traversing the neural network from the end. So we look at the output neuron and then look which neurons did contribute to this prediction the most and traverse that until we get to the individual pixels in the beginning or maybe pixel groups in the beginning. And then it differs on some mathematical properties when going through the neural network that I won't go into detail here. But as one can see, so these are all different saliency maps for the same image and the same prediction. So we still have this image of a dome that also has a prediction of a dome. And here we can see, for instance, that for guided backpropagation, what's important is that basically this, I hope one can see it, that the shape of the dome is highlighted. At the same time, here it's very obvious with the heat map. So the dome is highlighted. So this seems to be like a prediction that makes sense, or that at least we can see that the AI looks at the right place. There are many examples. For instance, if we imagine or that there were like many examples in the literature where basically, for instance, the AI was trained with watermarked images, so that basically you had a text here in the lower left corner or somewhere else. So this was very prominent for horse images. And then by having such a kind of heat map, one could see that for the horse class, basically the AI always looked like in this lower left corner and not at the actual horse. So by having these kind of heat maps, one can already, like in some cases, debug the AI system and see that there's something wrong with the training data. So these are different saliency maps that, most of them are based on some kind of backpropagation, so traversing the neural network, from the end. Then for many of these approaches, they are like continuous improvements. So we have like a very famous approach is GradCam, and later on it was like GradCam++ was developed, or ScoreCam, that all had like different ideas. So in this case, this looks like a little bit different than the original image, because to better see the differences, I've condensed the heat map. So here one can see that like the importance slightly changes in this lower right corner. Okay, so here it's significantly more focused on this lower right corner than in this first image. Okay, so they're basically like small varieties of these different approaches that are continuously developed to make up for some shortcomings. And other approaches, just to maybe go into one. So one of the first ones was vanilla backpropagation, and other like guided backpropagation builds up on that, because for this vanilla backpropagation, one can see that it's very hard to interpret these saliency maps. So yeah, we have like highlighting, yeah, nearly everywhere in this image. But it's like very hard to interpret what that really means. Okay, so is it now like a correct prediction or not? So is the AI correctly working or not? Because it's like very, yeah, very diffuse. Yeah, and just to round it up, so for instance, yeah, these, like I said, so all of these are local approaches. All of these are post-hoc approaches. Lime is model agnostic. These chem-based approaches are model specific, so they all depend on convolutional neural networks. Yeah, and vanilla backpropagation is also model specific. Yeah, integrated gradients is like a different approach, so this is not model specific actually, but yeah, okay, I won't go too much into details here. Yeah, so these are like more traditional approaches. I want to show you like a few other ones. So there are actually also approaches that work on other approaches. So there's this called approach smooth grad that actually takes, yeah, so for instance, integrated gradients or vanilla backpropagation and tries to augment these augment the explanations that are given by these approaches. So yeah, just remembering here, the map of vanilla backpropagation is like very confusing or hard to interpret. And after applying smooth grad, we can see that vanilla backpropagation seems to do its work because the yeah, because the dome is really highlighted. Yeah, and the idea of smooth grad is basically that one yeah, does not only use one classification, but one has the same image, introduces noise on the image, does the classification, and does the saliency map of the image, and then interpolates between these saliency maps. So you basically yeah, have a slightly different image all the time that you classify and that you create the explanation for, and then you interpolate between these images to, yeah, to just like find out the most important pixels. Yeah. Now, something completely different is feature visualization. This takes a different approach and basically is about visualizing what the different layers of an AI have learned. So I mean, if we, yeah, if we go a little bit into the technicalities, I mean, it's often that like these earlier layers in the neural network that they learn abstract concepts like filters. Okay, so here we can see like the progression. So for instance, in this fifth layer, it's like a very abstract what is learned. In layer 6, it's already like a little bit more concrete. So this seems to be like a little bit woolly or something. And in layer 7, I always think that it looks like ropes. Yeah, so here one can basically, the idea here is to try to maximally activate layers in a neural network by randomly refining noise. So one starts with a noisy image and then looks whether changes in the noise activate the layer in the network more or less. And then one gradually refines that until one has, yeah, basically these kind of pictures where layers in the neural network are completely activated. So yeah, and this is kind of, yeah, one could say that this is even a global approach because it tries to explain the neural network as a whole. Yeah, but it's still model specific and post hoc. And finally, one of my favorites is testing with concept activation vectors. Here, the idea is that a user that a user can define concepts that they want to test the importance of. So for instance, if I have the image of a zebra, then I want to know whether the concept of being striped plays a role for for the classification of the neural network. So in the ideal case, we would say, okay, yeah, zebra is striped, so we want that the concept of being striped plays a role for this classification of the zebra being classified as zebra. And this is basically what this approach can do. So here I've done it basically again for the dome with like a few random things. So for instance, I had like the concept female, and it doesn't impact the classification of being a dome, which is good because has nothing to do with each other. On the other hand, the concept of sky and the concept of being round play a role. So yeah, here we can imagine, okay, a dome is often like photographed against the sky. So in a way, it makes sense that the concept of sky plays a role. And yeah, and if a dome is like a semicircle, the concept of round should play a role too. And here, yeah, and so this seemed to be like good results for this kind of neural network. At the same time, this can also be well used for identifying stereotypes. So for instance, I mean, if we have in the neural network the class of basically yeah, okay, I'm missing the English word, like the person who is cleaning a room, and then query whether like the concept of female or the concept of male has a higher impact on this class, then we can see whether like this whether the training set was biased or whether the training set, good. So I've already told you about that there are three important distinctions. I did an analysis of taxonomies of these kind of explainability approaches and created my own taxonomy. And basically, yeah, we have the scope, the stage, and the applicability distinctions. But yeah, it's also interesting to look at what the result is. So when I use the explainability approach, does it give me a surrogate model? So this is what I said is often done for global models, so that I try to then create a decision tree to explain the original model with that. Is it such a kind of feature relevance explanation that I just shown you with the saliency maps? Or some approaches try to give examples or try to distill examples. So yeah, for instance, like these feature visualizations could be seen as examples. On the other hand, one could also look at how does the explainability approach work? What is its functioning? There we could see like structure leveling. So this is basically what I also said about this backpropagation. So we traverse the structure of a neural network to uncover information about it. Other ways to receive this kind of information are perturbations. This is how LIME works. So basically by disabling these kind of superpixels, their impact is tested. So whether they make an impact on the classification. And yeah, in this way, basically we can extract information about how important certain parts of the image are. Another way that I didn't show in an example is architecture modification. So here the idea is to, for instance, slightly change a neural network to make it more understandable or to prepare it for other explainability approaches. And meter explanation is this kind of approach that, for instance, SmoothGrad does, where it takes other explainability approaches and tries to augment them. And then one can also look at what is the output format. Is it like numerical? This is often what these saliency maps put out. You just get a numerical value of the importance of each pixel. Do you have like a rules? Is it textual explanation? Is it visual? Is it like mixed visual and textual? Do you get arguments, or is it like a decision tree? So another model. So this is basically a little bit of the taxonomy of what kind of approaches there are out there. And just to give the open question with regards to these approaches. Yeah, then the question is a little bit how to find out which explanations are needed in which context. What's often a problem is that, I mean, you saw it a little bit with the saliency maps. So you normally, when you use an explainability approach, you get one-shot images. So you apply the approach and you get one image, then, or you get like one output. And this does not always help you. So in this case, this does not always help every stakeholder that might be interested in information or that might be interested in understanding the system. So one could argue that like these saliency maps, especially like the one like vanilla backpropagation, is very hard to interpret, even for experts. So how should laypersons interpret that? And here the idea is, okay, how do we design interactive explainability approaches that can like adapt more to the needs of individual stakeholders? So do we just need to maybe combine the outputs of several approaches, or what could be other ways? How can explainability approaches and human work best together? So how can we maybe enable like human in the loop approaches? And how can we take into account the stakeholders' background? Okay, yeah, those were the open questions. And what I forgot, I wanted to, I mean, here we can see a little bit, so this output format, I mean, this is basically how computer scientists classify explanations. And I mean, this is different from what I've shown you on the slide on explanations before. So, I mean, here, another question is, how we can like maybe merge these different views on what explanations are. Good. So back to the model, we've now completely traversed it. And this is why I want to like go a little bit into the broader field and talk about open challenges. So AI is an ever-evolving field, and likewise XAI is. So one challenge is how to create explanations for new types of AIs. And I mean here, for instance, one question would be linked to large language models or transformers and generative models. So this is like still an open question with where no real approaches are on the horizon. I've sometimes hinted at this problem that there are many different disciplines involved in XAI that use many different and sometimes even have their own idiosyncratic use of terms. So we can find terms like interpretability, explainability, perspicuity, transparency, scrutability, causability, all sometimes meaning the same thing, sometimes meaning completely different things. And I've already also said the same for the desiderata. So some people say, okay, we have to improve the performance of the system, and they mean just like the accuracy. Some people mean with performance like the human-machine interaction performance. And then things get messy. And another thing is that basically, I mean, an open question that haunts many disciplines for ages is what exactly understanding is. And so the question is a little bit, can we at least come up with a useful account of understanding for the debate in XAI? One thing that I've also engaged with a little bit is how do we evaluate the quality of explainability approaches? Because there are many different approaches to that without real without really a gold standard. So it's unclear what we should look at when evaluating explainability approaches. Should we look at the quality of information? Should we look at the at certain mathematical metrics? So whether this explainability approach really captures what the AI system is doing, because in many kinds of approaches, this is not given. So for instance, this is like a problem for many model agnostic approaches because they do not exploit information from the model itself, but only from like analyzing it from an outside perspective. It is not guaranteed that the explanation that is given by an approach really corresponds to why the AI system did a certain prediction. Do we need do we need studies with humans to evaluate explainability approaches? Then what do we evaluate in these studies? I mean, do we just focus on the satisfaction of desiderata, because that's basically how I motivated the whole thing. But yeah, so there's no gold standard, and many people are wondering what to do about that. And finally, XAI does not only have positive sides, but it can also be used for negative sides, for negative purposes. So, for instance, if there are studies out there that basically show that if one gives an explanation, even one that does not really explain anything, but that just looks like a justification, or that just looks like an explanation, then people already trust the system more and are more likely to use a system. So explainability can also be basically abused by people that want to have their product out there. I mean, it can also be abused as a label. Our system is explainable, so buy our system and stuff like that. Another point on another issue is to avoid overly persuasive explanations. So, I mean, I've said that, for instance, for trust, we don't want that the user overly trusts the system, but we also do not want that they trust it too much. That's the same, but that they don't trust it enough. So we want that their trust is calibrated. And I mean, it can be that by giving overly persuasive explanations, the level of trust that a user has is not adequately calibrated, but they basically maybe overtrust the system because the explanation was just too persuasive. And there's like this question whether there's a performance explainability trade-off. So that basically, one has to sacrifice performance if one wants to make a system explainable. But the question is a little bit like, does this only hold for under-hoc explainable models, or even like for post-hoc explainability? I mean, these are a few of the questions, and I believe my time's up. So I'll go to the last slide, and thank you for your attention. So if you are interested in talking about or collaborating on one of the topics I've shown you, or any other topics on XAI that I've introduced, or AI ethics more generally, you can. I'm happy to welcome contacts or inquiries, or like any kind of collaboration. I mean, I believe my address is also like on the web page, or I don't know, but at least it's just you can look it up and it's here. So yeah, please contact me also if you have questions, but I believe we still have plenty of time for questions now. And with that, thank you for your attention, and up to the questions.
Okay, thank you for the talk. Wow, it's a lot of information, and honestly, I was overwhelmed by the breadth of this field of explainability, and it's very informative.
Good, thank you.
Okay, raise your hand if you have a question. And also,質問、日本語でしていただいても結構で、その場合は、私ができる限り通訳をいたします。オンラインの方、質問があれば、これを上げてください。そっか、マイクが必要だ。どうしよう。考えてなかった。いいよ、これを持ち運ぼう。これを持ち運ぼう。はい。じゃあ、これを。はい。じゃあ、こういう話してるから聞こえる。わかりました。
Okay, thank you for your talk. I could learn about complexity, or the mapping of the explainability of AI, but yeah, the customer said it's very overwhelming information. So I could follow the old information, but I'm curious about the connection, the difference between the like understandability of AI in the design or objective level and the like subjective level people have. I think like ability or interest for AI, will be depending on the person what background they have, cultural background, economical or linguistic background. So it might be like affecting to the understandability, like the difference in background. So how should we think about the like connection with differences about like how should we design understandable AI, or how to like promote to the understandable AI to the person like who have a different backgrounds? Yeah, that's my question.
Yeah, I mean that's basically one of the questions I also raised in the in the presentation. So basically, this is even like it was already overwhelming, and this was just like a simplified model of explainability that I've shown you, because basically you can always hook in this context. So like each of these relations between you can always put like the context in the middle, like always like the background of a person will facilitate how well an explanation facilitates understanding. And to the background of a person comes like how much they are involved in AI, whether they have knowledge about it, what their culture is. And so I'm not a psychologist, so I'm sorry I cannot really answer your question. But the goal would be to find out what these personal backgrounds, how they influence how understanding is facilitated in a person, and would be to find out which kind of explanations we need to deliver these persons to best facilitate understanding. Okay, so yeah, it's a good question that I also want to have answered, but that basically is very hard to answer, because there are like so many factors that might influence how a person comes to understanding, and how a person perceives and processes an explanation, that it's
So I think some people are easy to like use AI without comprehensive understanding of AI, but at the same time, some people who have different background cannot trust AI without understanding of comprehensive understanding. For instance, like some people are afraid of like using like AI machine like without understanding what inside of that. But some people are not care about it. So I'm so curious about that, subjective.
Yeah, I mean, that's again like another interesting aspect. I mean, we have these psychological phenomena of algorithmic aversion and automation bias, basically. So I mean, those are, I hope I'm correct, but these are like the technical terminals for these phenomena you've described. So basically, algorithmic aversion is that people just don't trust any kind of algorithm, even if that not trusting is not justified. And automation bias is that they overtrust systems, because they say, okay, yeah, AI is super, AI will solve our problems. And I mean, in these cases, it's always a question. I mean, we do not have to have people understand AI in all cases. I mean, as long as all goes well, maybe we don't need it. I mean, in other cases, we might want to educate people to use a system to reduce their algorithmic aversion if it's unjustified. And in other cases, we might want to push them to listen to explanations to correct their automation bias, to lessen their overtrust in the system. So yeah, again, it all depends on context, and it also like depends really on whether it's really a case where this has an important impact or not.
Thanks so much.
Yeah.
Take one question from online and then.
should I?
Yes. 宮西さん、どうぞ。
sure.
Have you? Should I
wait a
enable
second.
my?
Maybe I'll turn it on. すいません。
Or-
スピーカーがついてなかったので。
Wait a second.
Thank you.
どうぞ。宮西さん
Thank you.
どうぞ。
Thank you. So, 聞こえますか？
聞こえます。
ありがとうございます。So thank you for insightful talk. So I have two questions. One is that I recently happened to know that there's a field called mechanistic interpretability. So my question with this regard is that do you think the mechanistic interpretability is also a subgroup of XAI or not? Because as you noted, explainability and interpretability looks quite similar concept to me. So that's one thing. And another thing is that one challenge is XAI for the recurrent emergence of gigantic models like here comes GPT-2 or GPT-3 and GPT-4 and everything. And also the tasks are getting more complicated, like there's a big bench or the LLM bench or such difficult tasks. So from the XAI research perspective, how do you deal with the scalability of the XAI approach? Like what kind of method could be scalable, or what kind of research design could be scalable to big model, or such kind of things. So that's my questions.
Yeah, thank you for the. Oh, is up?
Yes.
Okay. Yeah, sorry for the hiccup. Yeah, thank you for the questions. Those are good questions that actually relate to each other, because
Yeah,
I
right.
would count mechanistic interpretability as a sub, as belonging to XAI. And I mean, so I like to talk about explainability because I mean, it's often a kind of cultural thing. So my background is in like many who have like more of a social sciences background tend to talk about explainability, and many people who have more of a computer science background tend to talk about interpretability.
Mm.
So yeah, for me, explainability and interpretability are belonging closely together, and mechanistic interpretability thus also. And yeah, I think mechanistic interpretability is a very interesting approach that can scale to LLM. So I think that actually you've maybe even answered your question a little bit yourself, because because I think that mechanistic interpretability is like a good starting point for explaining LLMs and like these always bigger getting models. But yeah, I think there are like also other potential approaches that might still have to be developed. Yeah, and I mean the question also is whether, so what kind of explainability we want. I mean, if we want local explainability, then maybe an explanation for such a big model is not so much different from an explanation for like new normal deep neural network. Yeah, but if we want global explainability, it gets increasingly complicated. Yeah, but that would be my yeah.
Okay, thank you very much.
Okay, and escape.
Hi, thank you for the talk. I have two questions. First one is not the expert in this field, so it's a bit naive question, but is there any kind of a difference in, for example, why we need more explanation for AI? You know, like we also have a lot of machine, like computer. I don't even know how it works in semiconductor level, and that's do we really need like this detailed level of explanation for? I mean, especially like a current AI. Yeah, that's the first question.
Yeah, maybe that's actually not a naive question. That's a very hard question, actually. I mean, I think there are several reasons. First thing, I'm not completely convinced that we don't need an explanation of how our computer works, even if we might still do well without. But I actually published a paper on why we should maybe even explain our microchips. But I mean, that's not the main answer I want to give. Maybe what's more interesting is that, I mean, two things. First, your own computer is not, I mean, it's not in this way a decision-making process, in that you get subjected to it and might not get a loan, or might not get advisor, or not get or might be sentenced in court more. So in this case, I would say that we need more of an explanation, or we need an explanation, because AI systems are used for these kind of decisions, which is, I would say, different than before, because before, I mean, we used maybe a computer to make these decisions, but that was only like because we had Excel tables, and it was still like the human that did the final decision. But now we have like an artifact, a technical artifact that basically maybe does this decision alone. So this is like the one facet. And the other facet is that in principle, for many, I mean, in principle, you could learn how your computer works, okay? But for neural networks, that's not, that's questionable in some cases. So, I mean, these systems are getting, or these models are getting so complicated that, that basically, it's not guaranteed that we can still explain or that we can still, understand them. And so I would say that this also prompts why we should try, so that we don't end up in a society where decisions are made over us, or made on us, that about us. I search for the right preposition. Are made about us without us understanding why.
And second question is actually related to your answer now, but the other example you use is like convolutional neural network, and like a supervised the learning, and you can see like which area of the image, for example. I know that's the example, but again, just visualize which part of the image data is being interested by AI. But I wonder, to me, this kind of supervised learning is more, at least we know the objective. We give them we give the neural network the goal objective. So it's more like, to me, like those explanations, like how to process to achieve certain goal. And I feel, we need sometimes that level of explanation, but I wonder, is it more, I mean, you actually at the end of the slide, you said like, how about LLM, or, new type of AI, like these, generative AI doesn't really have I mean, the goal is actually predicting the next word, but somehow it's just doing something like, looks like agentic now. And maybe in the future, it's more like we might create the AI which actually can make a decision. I mean, can set their own objective. And I wonder, like, do we actually, I mean, can we actually understand when we actually create AI which can set its own goal, how we can actually understand? They even, they might be already beyond the explanation, I would say. So what do you think? I mean, your approach, I can understand that can be applied to the current AI, but in the future, if the true agentic AI achieved, maybe it's getting much harder to understand what's actual.
Super question. Yeah, it's a very good question. Yeah, I mean, so basically, I always think that there are ways to extract information from these systems. Okay, I mean, what then might be the question is whether these systems are maybe thinking or acting in concepts that are so so far away from the concept that we use for our thinking that there is no alignment possible anymore, so that we don't basically can think in their goals anymore or something like that. So this is why somewhere how I can imagine maybe your question aims at. Yeah, and then I mean, maybe then the goal is not anymore like really extracting this information, but trying to maybe educate people on acquiring these new concepts, or trying to still trying to simplify these new concepts so that we can still understand them.
The human also step into the
exactly. So I mean, this is like, but some people claim that like this new agentic AI would bring like a new breakthrough for human understanding. So yeah, I mean, maybe then the goal would shift more to like this kind of alignment between. I mean, I'm not a fan of speaking of AI alignment, but of this kind of alignment of concepts between humans and AI.
I like the idea. Yeah, thank you.
Okay, any other questions? No? Maybe I'll ask a few. Yeah, I got a list.
Okay.
Yeah, but one thing is very similar to what Keisuke asked, actually. So about whether we need explainability at all. And so you said that so we want explainability to meet these desiderata, lots of them. But in all cases, is there any specific desideratum that necessarily requires explainability? Because otherwise it looks like you can just skip explainability and just go for the desiderata, like fairness, without explainability seems like at least conceptually possible for me. And is there any like specific desideratum that for you seems like requiring explainability when you say because you said that explainability actually is very much needed?
Also very good question. So you're basically giving actually one of the main criticisms on the whole explainability project is exactly that one. Yeah, I mean, actually, I think it's hard to really say whether a certain desideratum really needs explanation. So I mean, I've written an article where I defend the position that it's co-written an article where we defend the position that it's that you basically need it for responsibility attribution, so that the best way to have responsibility attribution for these AI systems is with certain kinds of explanations. But I would say what maybe is more interesting of an answer is even if it turns out that we don't need explainability for any of these desiderata. So I would say that I don't know another way that at least might cover as many desiderata. Okay, so I mean, the question here is basically, does it require more effort to invest into explainability as a means to these goals? Or is it easier to basically create a solution for each goal on its own? So, I mean, this would be like then the question that one really has to ask. And I would say, or I'm optimistic at least, that explainability is a good way to go, because you might have recurring patterns that that certain desiderata need like a specific kind of information that you can provide with explainability, and that this pattern recurs and that reoccurs, and that you basically then already have like certain paradigm case from which you can work on. And so I think that this is maybe the argument that speaks in favor of explainability.
I see.
Yeah.
Maybe one more question. So this one's maybe easier to answer. So it looked like, to me, the kinds of explanations that you presented today are mostly tuned for like designers and developers in terms of the stakeholders. And I'm more in the user group. And like, given that saliency map doesn't mean much for someone like me.
Yeah.
So maybe this is similar to Hayata's question, but for users, so one question is it right to understand that this research is mainly targeting these stakeholders, designers and developers? And another question is, what are the like proposed approaches to address the user group?
Yeah, again, very, very good questions. So, I mean, I've spoken in my talk like a little bit about that there's this disconnect in disciplines, and this is really what you where you notice this with this question, because I mean, all these or many of these approaches were developed by computer scientists for computer scientists. So just as you've noticed, and and like this whole research on explainability started basically with this rush on, we need to explain AI systems, or we need to debug AI systems. So the desideratum that was most often demanded in the beginning was basically debuggability, to increase accuracy. And so people noticed that there's a disconnect, and then social scientists came on board. But I mean, it's hard for social scientists, again, to develop any kind of technical approach. Okay, so so I would say that basically the goal would be that we need this kind of collaboration, or we need some kind of collaboration between computer scientists that can develop these approaches, and social scientists that maybe tell us what type of information we need, what type of explanation we need. And and I think that this is ongoing research, and this is open research. And I mean, this is also why I highlighted in the beginning, when I have shown you basically this huge table, that these were mostly computer science paper, and they basically didn't investigate whether there are claims that that explainability will contribute to this desideratum, whether this holds up. So so I would say that we need much more also empirical investigation of whether the claims hold up, and also philosophical and legal people that might tell us something about which types of explanation could be useful, what desideratum, whether a desideratum is justified, and what we might need as a condition for desiderata satisfaction, and all these kinds of questions. So basically, I think that's still an open gap in the research that direly needs to be filled. And also, like the taxonomy I came up, I mean, I've noted a few times that there's like this disconnect between how maybe philosophers and other scientists see explainability and how computer scientists build it up. And so I think it's very, very important to reconnect that. Or I mean, you can only reconnect something which was connected. So to connect it the first time. So
Okay, thank you. So it's time. So let's thank the speaker again, and maybe myself, only me.
Thank you for the invitation. It was a pleasure.
Okay, so This is the end. 最後に、次回のチェーンセミナーについての、告知だけさせてください。共有ができない。画面共有がうまくできないな。画面共有できないので、口頭で言います。8月の20日に、第45回のチェーンセミナーで、細田光先生の、生物とロボット、柔らかさと知能というテーマで、講演をしていただきます。ウェブサイトで、ホームページで、また詳しいことは、掲載されているので、よろしければそちらをチェックして、ぜひご参加ください。では、本日は、教室の皆さん、オンラインの皆さん、ありがとうございました。これで終わりにします。ありがとうございました。